Thanks for introducing me. Hi everyone and welcome. In today's webinar, I will talk about the inversion-based horizon tracking algorithms and show you how to quickly create a continuous horizon in challenging settings that requires little to zero editing. In OpendTect, we created several tools for horizon tracking. You can auto-track horizons in the 3D scene, or you can also follow a more conventional approach and track horizons with the help of 2D viewers and the base map. And on top of that, we have the Inversion Tracker, formerly known as Unconfirmity Tracker, which can generate one or more horizons from a seismic deep volume using a constrained inversion-based algorithm that globally minimizes the error between horizon deeps and seismic deeps. And then we have Inversion Plus Tracker, which goes beyond that and combines inversion-based flattening with event correlation. Both these trackers use inversion-based techniques that aim to flatten the seismic deep field. The specialty of the Inversion Tracker is that it does not operate on seismic amplitudes, but instead uses the deep field as input, so it's capable of mapping, for example, unconformities, which cannot be mapped using a particular peak or trough and are characterized by a variable seismic character throughout the whole survey. On the other hand, it can be a disadvantage of the flattening method if, for example, we want our horizon to exactly follow a specific seismic event. If that's the case, OpendTect has a solution for it, which is called Inversion Plus Tracker. We also call it a hybrid algorithm as it combines flattening with event correlation. As you already noticed, the two algorithms have a lot in common. Both use the inversion-based flattening. Inversion-based flattening, what it means that an initial horizon grid is constructed, it's shown on this top image. The initial horizon grid is constructed through one or more manually picked seed positions, and after which an inversion algorithm minimizes the error between the horizon dips shown in blue and the seismic dips shown in orange. This is done with the constrained conjugate gradient solver, and after each iteration loop of the solver, the horizon grid is retied to the input seeds. Optionally, you can also include a third component called planarity, which is a kind of confidence cube for the seismic dips. It's a way to include faults into the horizon tracking without actually picking the faults. Planarity is a measurement of the local curvedness of the deep field normalized between 0 and 1. High planarity corresponds to good reflections, and low planarity occurs near faults and in noisy sections. Planarity is used by the inversion algorithm to assign higher weights to areas with good reflections. On top of that, you can also provide the actual fault planes. In this case, the algorithm will calculate fault dips and update the steering cube and the planarity cube. And yeah, we talked about the similarities, and I wanted also, of course, to talk what differentiates the inversion tracker from the Inversion Plus tracker. On this image below, you can see the result of the inversion tracker. The horizon grid is tied to manually picked seed positions, which are over here in green, and these green dots and the white dots are auto-generated seeds added by the Similarity-based auto-tracker after each inversion cycle. The Similarity-based auto-tracker firstly snaps these green dots to the nearest seismic event. And then the tracker compares amplitude differences and cross-correlations between seed traces and traces located at the edge of the growing horizon grid. If the difference is less than the similarity threshold, then the acceptance criteria are met and the positions are added to the grid. In the Inversion Plus algorithm, the decision to add seed positions is based only on cross-correlation threshold. On this scheme, you can again see what both trackers have in common and what also differentiates them. The common parts are the gray boxes, and the part which belongs to only the Inversion Plus tracker is in yellow. So first, both methods start with the manually picked seed positions, and the horizon is constrained with these picked positions. But in contrast to the inversion-based flattening or deep only, the hybrid algorithm snaps as a second step, it snaps these positions to the nearest event, minima or maxima, and then the initial horizon grid is constructed through the seed positions, and the conjugate gradient solver is started. And after each inversion cycle, which ends here, the Similarity auto tracker kicks in to add additional seed positions. And the horizon grid is tied to the new seeds, and the process continues until the end criteria of the inversion loop are met. Here on this image, I wanted to show a comparison between the three tracking algorithms. In the blue cyan color, you can see the result of the simple auto tracker, the similarity-based auto tracker, and in yellow, it's the result of the inversion tracker, and the inversion plus tracker horizon is shown in magenta color. All three algorithms used the same set of input seeds, and both inversion-based algorithms use the same parameters for dips and planarity, and for the conjugate gradient solver as well. You can see that the similarity-based auto tracker had quite some loop skips. Of course, this can be reduced, but at the expense of creating larger holes that the user would have to fill in later. And you can see that the Inversion Plus tracker shows better results of following this white loop over here. And yeah, before we go to OpendTect and see how it actually works in practice, I wanted to say a few words about what's coming to OpendTect soon. And it's going to be a new Horizon Cube algorithm which deploys this Inversion Plus tracking workflow. So as always, for the Horizon Cube, you'll need to provide a set of framework horizons. These framework horizons can be either picked using one of the algorithms that we already discussed, or can be imported from the other software. And in the next step of this workflow is to add anchor horizons under user supervision. This is done per sequence bounded by two framework horizons. The workflow is similar to the one that we already discussed. The inversion-based algorithm is run either using deep-only method or the hybrid method, and the results are QC'd, and the additional seeds can be added if necessary. And this workflow is repeated until the user is satisfied with the anchor horizons. And of course, the algorithm takes care of the horizons being continuous throughout the survey and not crossing each other. And in the third step shown on this image here, the more horizons are added, and these last horizons can be added by using either the inversion or inversion plus algorithms, or just model-driven infill where the horizons are proportionally inserted between upper and lower boundaries. And what is special about this whole upcoming horizon tracking, horizon cube algorithm is that the user has an opportunity to add more control points to any of the horizon cube events, even to those added at the very last step. So full control and good results are coming. And now I'm going to switch to OpendTect window. And here I have the F3 demo dataset and the 4 wells. And I'm going to use the Inversion Tracker, which uses the deep field only to track an unconformity, which goes through this red marker called top 4 sets. This red marker starts from here and goes all the way down here. So unconformities are surfaces that are not well represented in terms of a specific seismic phase. But the advantage of the unconformity, the inversion tracker, is that we can indirectly extract such information from a deep field. On this section, we have a nice example of clinoforms, and here and at the base of this package, a lot of reflections merge together, and it's a challenging task to map this kind of surface using the conventional tracker. But by inverting the deep field, we can actually achieve that. And also, I must say rather quickly, and what I'm going to show now is a bit out of the scope of this webinar, but here's an attribute extracted from a horizon cube, which is called horizon cube density attribute, and shows the how many horizon cube events we have per time window, and this attribute can actually demonstrate this kind of unconformities, which are easily distinguishable in bright colors, where the horizon cube density values are high. I'm going to switch this off and now show you a horizon which was tracked from these well markers. To actually do this, you'll need to right click on the 3D horizon, go to new, track using inversion, and over here we have an icon called from wells. By clicking on this icon, you'll get a dialog where you need to select a marker and the wells from which this marker will be used. I'm not going to do it now because I already pre-processed this horizon, so I will just display it in the scene. Here's how it looks, quite smooth, and I'm going to click the V shortcut on the keyboard to display it on sections only. And as you can see, this horizon is snapped to all the well markers, and you can also push the seismic sections back and forth to QC it in all directions. It's a random line, so it's quite easy and fun to use it for QCing purposes. Yeah, looks quite good, and of course at any time you can go back and add manually picked positions to this and produce even more precise surface. And now I'm going to use another data set to show the Inversion Plus tracker. And here is a data set from the Australian North West Shelf, and you can see that it's a highly faulted area, and what I'm going to do is actually to pick this red event over here using the Inversion Tracker. And for this, again, right click on the 3D horizon, go to new track horizon using inversion. Here I have a steering cube and the input seismic, of course, because it will also take the seismic amplitudes into account. And I'm going to create a new horizon and add an empty point set. And I'm going to grab this icon called pick seats to actually pick a few seats along this section and to run the auto tracker. Maybe the color yellow is better. And I'm going to drop a few seats, with, especially near the faults, so that give a little help to the tracker. And I'll have a quick look at the processing parameters. Here I'm using confidence weight, which is planarity. That's what we already discussed. And I'm going to quick run and see how the tracker works. It shouldn't take too long. It's really quick process of creating a new surface out of a few seat positions. And yeah, let's see how it works. What I wanted also to highlight here that it's an iterative process. So okay, it's done. I'm going to put this window aside and see if I need to do more iterations and to add more seats to the horizon. It looks already quite good. I can see that the fault blocks are tracked quite nicely. I'm going to click V on my keyboard and to press space to switch from the pick and seed mode to the cursor where I can actually push my inline back and forth, and I can see that around the inline around the middle of the survey where I picked my positions, the horizon looks good, but as we move away from these positions, of course the fault blocks are not honored as nicely. So what I'm going to do is actually to get back to this window and continue picking more seats. For instance, I wanted the seat to be here, and also, oops, not this one, control click to remove it. For instance, I would definitely add more seats over here, but I'm not going to bore you with myself picking the seats in this webinar, and I already did it. I added quite a few seats to point set, and I'm going to show it right here in this magenta color. You can see I picked quite some seats throughout the survey, and I'm going to feed in this point set into the Inversion Tracker and run and create another horizon with the very same processing parameters. I already did it, and let's see how it looks. I will just override the this yellow surface which I just created. Again, shouldn't take too much time, and I'm quite sure actually that the new surface will come out much better. And yeah, again, as I already mentioned, it's an iterative process, so you can drop one seed and run the inversion plus tracker and see the result, or then you can add a few more seeds and see the results, and then maybe you'll need to add many more seeds to achieve the satisfactory results. But again, it's much faster than using the conventional auto tracker and then do the editing afterwards. Okay, it's finished. I'll close it and close this window as well. Switch off the point set, and yeah, looks good. You can see that many folds are nicely tracked. And again, of course, I'm going to display this horizon on LED sections and probably also switch color to yellow and see how this looks. Yeah, it's much better. As you can remember, towards the edge of the survey, the folds were not honored, but because I added more seeds, and now this looks much better. And yeah, that's how the inversion and inversion plus work. And this is my last point. And thank you for watching, and we open the floor for questions.